Good morning, everyone, and welcome to the second installment on the telescope, our final one. Today, we'll focus mostly on the evolution of the telescope through time. And as I mentioned last week, our speaker will drop a few names that you're familiar with and a few that you may not be familiar with. My name is Louis Morel. I'm a member of the Science, Medicine, and Technology Curriculum Committee, and our team is happy to bring you this session today. Because they are such a distraction, if you haven't done so already, please silence or turn off your cell phones. Welcome to those who are joining us via Zoom. Our technician today is Mary Ellen Mayulo, and thank you for helping us have this hybrid modality. During the presentation, you may ask questions. Raise your hand. I will bring the microphone to you before you ask your question so that everyone, especially those online, can hear it. And finally, next week, Thanksgiving week, there will be no activity here at HASP, so the office will be closed next week. So hopefully everyone will have a fulfilling holiday. Thank you. Yes? Oh, yes. Well, it'll be closed Wednesday, Thursday, and Friday. Sorry. Yes. Yes. Thanks for pointing that out. A bit about our speaker. Our speaker's interest in astronomy started at a young age in elementary school. It was a field trip to a planetarium that captivated his interest. And from that moment on, he read as many books as he could on the subject of astronomy. But unlike most youngsters, he added one dimension that most don't: building telescopes. He's been a member of various astronomical associations during his lifetime. For several years, he was chairman of the North Central region of the Astronomical League. He has participated in a number of research programs providing data to professional astronomers. This past summer, our speaker, Frank Roldan, went to the Kennedy Space Center in a teaching capacity, and perhaps we'll learn more about that today. Our speaker has been a member of the Shoreline Amateur Astronomical Association since 2007. The group is based at Hemlock Crossing, and he currently holds the position of observatory director there. Oh, and one more note on astronomy. I didn't take a poll last week, but I did mention that if you are interested in astrophotography, Mike Shaw's book called The Beginner's Guide to Astrophotography was published just a few months ago, and there's a copy available at Herrick Library if you're so inclined. Frank retired after a 38-year career in the telecommunications industry. And during this time, he held the position of technician, engineer, general manager, and regional manager. And he's also a veteran. He served in the US Army during the Vietnam conflict and is currently a lieutenant colonel in the Civil Air Patrol, the auxiliary force to the US Air Force. So please welcome our speaker, Frank Roldan.
Thank you so much, Louis. Well, thank you for coming back. I guess I wasn't too boring last time. So today we're going to get into what I call, let's go to that first slide. Hello. Okay, we'll go this way. Oh, that's not going to work either. It is on. Well, yeah, we set it up a little different. Maybe that's not going to work. So the notes are not advancing with the notes. Oh, okay. And that's fine. Yeah, the notes disappear, but I don't need them. I'm fine. We won't be able to advance them probably. Okay, let's see if we can advance. Perfecto. See, it's good to have an expert around. I just know enough about computers to get in trouble all the time. So we're going to have a brief history of telescopes, and it's going to be brief. We could have probably a whole semester if we were really to look at the whole development of the instrument. But so, okay, we'll start with this question. Who invented the telescope? Yeah, we got a spoiler because if you think that it is this gentleman, you are wrong. Galileo did not invent the telescope. A lot of people think that he did. So this is what happened. A gentleman by the name of Hans Lippershey, he was an eyeglass maker, okay? And he observed one day a couple of ladies playing with his lenses and looking out the window in the shop. You know, the old opticians were quite different from today's opticians. They didn't have all the equipment that they have nowadays. They simply had a selection of lenses and you play with them and say, oh, that works. Okay, that's it. We'll make your glasses. So that gave him an idea. Okay, when he saw these gals doing this kind of thing. By October 2nd, he had come up with a telescope and he went to get a patent. And I like the description of the patent, an instrument for seeing things far away as if they were nearby. His telescope, very simple, a convex lens and a concave eyepiece in a tube, and that was it. You know, I haven't been able to find out what the magnification of this particular instrument was, but it was low. I'm sure it was only like five times or something like that. Unfortunately, a few weeks afterwards, another Dutch instrument maker, Jacob Melius, also went and applied for a patent for a similar instrument. So the end result was that although Lippershey was not given a patent, he was hired to make a bunch of these telescopes for the government. But most historians do give Hans saying, yes, he was the first one who actually invent and make a working telescope. That is where they contracted him to make some copies. Oh yeah, the reason that they didn't give him a patent, say, well, by now we have several people who know about telescopes and how we're going to tell who really was working on it first, you know. So be it. Needless to say, the news about this device spread quite quickly through Europe. And of course, by 1609, Galileo heard about it. And definitely, needless to say, he was very interested in this device. And he started playing and fooling around. He went and bought some lenses from an optician. And he played with them. And eventually, he made a low power telescope of his own. In order to do the tube, which I thought was kind of clever, he had a whole bunch of straight pieces of wood, and he glued them to a piece of leather and then rolled it up. That's how he made his tube. So the whole telescope, and I'll show you a picture of it. It's all made out of leather from the outside. The one thing about Galileo, and that's, I think, why so many people think about it, he was probably the first one who turned the thing on the sky at nighttime. So he was an astronomer. Based on his logs that he kept, so one night he decided to look at Jupiter. If Jupiter was visible, he looked at it. He noticed some little points of light nearby Jupiter. He figured they were stars. He did make everything, every time he observed, he would make diagrams of what he was seeing. A few days later, he went back to look at Jupiter. And guess what? Those little points of light were in a different place. That really got him going. So he started observing Jupiter carefully. And he finally came up with the idea or that those points of light were moons going around Jupiter, same way that our moon goes around our planet Earth. Those 4 large moons are called the Galilean moons. And Io, Europa, Callisto, and Ganymede is the name of the 4. Today, the count for moons for Jupiter, by the way, is around 69. One time, the number was in the 20s. And then as telescope got better, the number kept going up. Hubble found a whole bunch of them. Some of them are little ones, okay? Then Nothing like the Galilean size ones, but yeah. Same thing has happened to Saturn, by the way. The number of satellites or moons for Saturn has gone up also in the 60s, I think, if I remember. Every couple of weeks, I'm reading one of these journals, oh, another one. So, now, the telescope that Galileo made still survives. It is in a place called the Instituto e Museo di Storia della Scienza. It's of Cornelius in Italy. In 2010, thank goodness, for those who don't speak Italian, they renamed the Museum Galileo. That is what it looks like. Small, probably it's about something about that size. And everything was, like I said, made out of leather and glued, and but it worked. It worked within the parameters that a telescope like that would work. One of the early problems with the telescopes, soon to be discovered as people started using them, was something called chromatic aberration. From the name, you can tell that chromatic has something to do with color, and aberration with something going the wrong or being incorrect. Okay, and what it is the failure of the lens to actually focus at the focal point all the different colors that make up visible light. Okay. And the reason for that is, after all, the light is going through this glass, that is what the lens is made out of, and different types of glass have different ways of dispersing light. Okay, and so these very simple lenses that had in those days, whatever the glass was made out of, didn't quite redirect the different frequencies of light to the same spot. So what it looks like is like whatever the image is that you're looking at seems to have around the edges like a little rainbow. Very annoying for when you're trying to do some precise measurements and so forth. Okay. Rule of thumb, something called the reflective index, meaning how much does this particular piece of glass or some other element, how much does it change the direction of the light as it goes through it? Okay. In most cases, in a transparent material, the index will go down, okay, as the wavelength of the light goes up. In case you're not familiar with it, visible light, the light that our eyes can see, has a frequency or a wavelength from about 400 nanometers all the way up to 800 nanometers. And a nanometer is roughly 0.003, I believe, of an inch, something in that neighborhood. So we're talking about very small stuff. You realize that there's light that our eyes do not detect, right? So the infrared beyond the or ahead of the red, we don't get to see that infrared. You're seeing going to a restaurant, they have these heating lamps in which they put the food so they don't get real cold before you get it, and it looks red, right? That light bulb is giving off infrared light, but then they put a filter on the front of the bulb so that you can see. It's changing some of that infrared to a red that we can detect with our eyes. At the other end, we got the ultraviolet. Anything beyond the violet, our eyes do not detect that. So, and here's a diagram again showing what happens with a simple lens where not all the lights will, all the colors will not fall in the focal point. So how do we fix that? The solution then was something to come up with something called a achromatic lens, okay? It is a lens that made in such a way, usually, so we're gonna see a compound lens with different materials are used, so one compensates for the other one. and then we can get all the light in the right place at the right spot. The simplest one is called a doublet because it's made up of two different lenses put together. Okay. And most of them use what is called crown glass as well as flint glass. So crown glass has a very low dispersion. Okay. As you can see, what the basic elements of that go into the making of this glass. Okay. While crown or flint, excuse me, is a higher reflectivity index. Okay. This AB number is simply German physicist came out with he came out with a way to have a scale to compare different reflectivities. Okay. Now flint again uses more like lead oxide, silica, and potassium in the mixture for the glass. But if you make a lens of each, and of course they have to be ground to match each other, and you put them together. I believe I have an here we go. We have a little. Can you see a line? Come on, everything is going to fail. Do they see that black line there? Okay, that's where the two different lenses have been cemented together. Okay, so one of those lenses is made out with flint glass, and the other one with crown. And what's going to happen is that they will focus the light in the proper place. Not all, sometimes we have triplets. Again, the optician that came up with this particular lens decided to go with a triplet. They're not always necessarily glued together. Some of them are air-spaced. Some of the very large refractors are usually air-spaced. There's space between the two elements or the three elements that make up the lens. I had a question, somebody one time say, oh, you must evacuate that space between the two lenses, right? It must be in a vacuum because you don't want air in there. And the answer is no, we can't do that because if you evacuate the space between the two lenses, the atmospheric pressure on the outside is pushing in on those two lenses and changing the curve. So somebody asked me one time, could they fill that space with like nitrogen, such an inert gas? And I honestly haven't been able to get a real answer for it. I am sure that one of the problems might be that even something like nitrogen has a index of reflectivity. I mean, it probably would affect the passage of the light. So if I ever get a good answer, I'll pass it along. But it makes sense to me that you're better off just having air in there and nothing else. And here, of course, the diagram now, this combination achromat puts all the colors in the same spot so that we can get the image with a funny looking rainbow around it. That was a big to-do in the development of the telescope. I mean, that was a big discovery. A lot of experimentation went in, and glass making has changed so much through the ages, compared to what they could make back in those days. By the way, who do you think were the best producers of glass for telescopes for quite a few years? Well, Bausch & Lomb in Germany, yeah, they made some good lenses. But the French, back in the 1800s, were the people to go to get a blank for a lens. They somehow had gotten the art of making glass down to perfected it. But yeah, Bausch & Lomb has always made some very good optics. And then Japan took over. Okay. If you notice that just about every except for some of the German cameras, I think just about all the other cameras were made in Japan. They really. And we're going to talk about them a little bit later on in a different way. So the largest refracting telescope, one that uses lenses that has ever built, is actually not too far from us. Okay, it is at the Yerkes Observatory, which is in a little town called Williams Bay. It's in Wellworth County in Wisconsin. And the observatory is on the northern shore of Lake Geneva. You ever heard of Lake Geneva in Wisconsin? Okay. Lake Geneva, back in the 1800s, well, even today, was kind of the playground for the rich folks that came from Chicago and other parts, because there's a lot of mansions that were built along the lake shore. Of course, it's still there. Wrigley, the famous chewing gum manufacturer, who also built the stadium right in Chicago, has a beautiful mansion there. So as I say, it's on the north side of the lake. It has beautiful grounds. Actually, you will see it's a beautiful building. It was completed in 1897. Okay, it belonged until fairly recently to the University of Chicago, the Astrophysics and Astronomy department. Okay, now you may think, why would Chicago University build an observatory in Wisconsin? One of their deadly enemies when it comes to sports, like the Bears and the Packers. Well, two things. Well, I mean, to build an observatory in downtown Chicago, even back then, was a waste of money because light pollution and so forth. On the other hand, that part of Wisconsin was pretty pristine. Very few houses, nice dark skies, fairly decent weather, and the other fact was that the astronomers at the university around early afternoon could jump in a train and be at the observatory by late afternoon to do the observing. They had a fantastic, as we did back years ago, we used to have a very good train system in the United States, in my opinion. Not quite anymore, but so that's what they did. They would jump, they would go do the observations. They had assistants who were there at the observatory all the time, so they probably call them up and say, okay, is it clear? Okay, we'll be there tonight to do some observing. Now, you ever heard of Charles Yerkes? Okay. Well, Charles Yerkes owned the streetcars in Chicago. All the lines were, he was a very wealthy man. He's supposedly, what I heard about him, kind of a shady character. He kind of underhanded when it came to making business and all that. So he was approached when this whole idea about this big telescope, and he says, it'd be nice if you could donate the money to build the telescope. You'll probably clean up your image with the folks because you're doing something for the community. So he actually went ahead and said, yeah, okay, I'll pay for the telescope. And once the telescope was in production, they came back to him and said, oh, by the way, we need a building, an observatory building to house the scope. Well, he paid for that too. So that's why we know it as the Yerkes Observatory, and it's referred to as the Yerkes 40-inch refracting telescope. Now, the idea to come up with this big telescope come from somebody you probably heard about, George Ellery Hale, very famous astronomer back then. He kept promoting building bigger and bigger telescopes because of the kind of research he was doing. We'll talk about George, I think, a little bit later on. Here's an aerial view of the observatory. The big dome is, of course, the home of the 40-inch refractor. The small dome to the back, this one here, today houses a 24-inch reflecting telescope. And this one here, a 40-inch, what if that doesn't come out? A 40-inch reflecting telescope. Over there, they always call this the 39-inch telescope, even though it's 40. And the reason for that is people kept getting confused with the refractor or this reflector, okay? People make appointments to use the telescope just to get there and find out that no, they didn't get the big refractor. They were going to be on the 40-inch. I'd like to show you a picture. You recognize this gentleman? Why am I having problems with my pointer? This gentleman right here. My battery, yes, see, that's him, good old Albert. you have to realize that when you build the biggest telescope in the world, everybody wants to, who is anybody wants to see it. So a lot of tours took place in the early years of the observatory. And definitely we have good old Mr. Einstein right there as a visitor. Now I want you to pay, the tube, by the way, of the telescope is 60 feet in length. It's the biggie. They're standing on a floor, big round floor, of course, that will go up and will go down by about 20 feet. Well, visualize this. Oops, my apologies. When this telescope is at the horizontal position, that eyepiece is going to be way up there. When it's pointing almost straight up, it's going to be way down, right? So in this picture, let me take a closer look. Pay attention to this area here that seems to have like a railing, which it does. It's kind of hard to see in this picture. All righty. Let's see about another shot. Okay, here is when they were building the telescope, assembling the pedestal on which it sits. This happens to be the polar axis. So this is the thing that will have to be aligned perfectly to the north celestial pole. They're not, 1800s, 1900s, actually, yeah, it was late 1800s technology, right? A lot of heavy duty machinery, gears, and so on and so forth. Well, let me go back. This beam here with those supports is that gallery that goes all the way around, okay? And we're gonna see a better, that's a telescope today. Right, this is the last time that I was there, those are the colors that they have painted. I don't think they have changed that. And there you see the gallery. And there you see the floors way down. So this whole floor can go even further down than this, all the way up to that gallery. Again, to compensate for the height of the eye. They do have, can you see there's a big ladder back here, a movable ladder? And yeah, you can use that to reach the eyepiece. But when you're trying to attach an instrument to the telescope, like some light detection or measurement equipment, that it can be there, so they're kind of heavy. Nowadays, they're a little bit lighter, but the early ones were pretty heavy pieces of equipment that were kind of odd shape and kind of hard to handle. You want to be going up the ladder with your two hands full of something to attach it to the telescope, so that making the floor go up and down made a lot of sense. During the construction, one of the cables broke, and the floor went kind of cattywampus. But then they were able to replace the cable and fix it. And okay, let me give you just a little word story, I guess. When I moved to Wisconsin, I moved to Milwaukee from New York City. I had enough of crowds and I wanted space. So off to Milwaukee, and you say Milwaukee is a big city. Well, it is, but not as big as New York City. And the one thing that attracted me, I did look for a lot of places in the country to move to. Milwaukee was extremely clean. That's what hit me right off the bat, how clean and well kept the city was, okay? And then, of course, I got a job there, and so off I went to Milwaukee. That's when I came across the Milwaukee Astronomical Society, the first amateur society. Up to that point, I really had been doing astronomy on my own, even though I did visit the Hayden Planetarium a lot. It became kind of my second home when I was living in Manhattan. One time, there was a gentleman by the name of John Briggs who took the job of observatory engineer at Yerkes. And when he found out about the Milwaukee Society, he joined us. And he was a great guy, very helpful, very knowledgeable. By then, I was president of the society. And I get a phone call from John one afternoon and says, "Frank, I got a problem with the telescope, and I can't figure out what it is." So we talked for quite a while. I said, "Okay, John, what is it?" "Well, I'm getting like a gear backlash on one of the gears for that big, actually for this for this axis right here. He was getting backlash. And backlash, you don't want a telescope because, you know, you center it, and when you lock it or something, the thing shifts on you, and now you don't have the whatever it is you're looking at. So I say, well, did you check this? You check that? Yeah. And I finally say, well, listen, I don't know what to tell you. This the same kind of stuff that I would check, but if you want me to, I'll come out here. I'll bring a couple of the old timers from the society who have been around for a long time. And he said, oh, that's great. Why don't you come over? So off we went to Yerkes. And make a story short, I tested everything that he said, and everything was fine. And then I said, have you looked inside the pedestal? And he said, no, I haven't. Nobody wants to look in there because, I mean, well, we've got 80 years worth of dirt and grease. And the motors for turning this thing are in the base, in the sub-base bit, okay? And then they have these shafts that run all the way up to the telescope to match with the gears and so forth. So I fortunately brought with me a jumpsuit. I had a hat on, I had gloves, and I went into that dirty area of the telescope. And I would say, John, okay, move it this way, move it that way, move it this way. And I was watching all those shafts because I figured the problem might be there in one of the connectors, and sure enough, you know what a pillow block is? Okay, some of you know about machinery. Well, if you need to have a shaft that is supported but it can turn, a pillow block is nothing more than a big bearing, okay, that is sits on a housing. So, and the housing gets attached to whatever, whichever way you're going to support it, okay? Well, I saw that one of the pillow blocks in one of the shafts, when he moved it, the whole thing was moving. The pillow block itself was moving. It was loose in its connection to this big structure. So I said, okay, I've got the wrenches. I went up there, tightened it up, got dirty, but that's okay. And the problem was gone. Well, John was delighted. He was very happy. I said, listen, anytime you guys want to use this telescope, just call me. If it's available, it's yours. So fortunately, I got to use the 40-inch refractor several times during my stay in Wisconsin. That was quite an honor, I think, to look through the telescope that Mr. Einstein looked through. The telescope, though, as great as it is, it takes several hours for it to really, when you open up that dome, can you see it on this picture? Yeah, these two big structures here are the slit. The slit is what we call the opening in the dome, so you can look out of it. This particular telescope, the doors open up. There's two doors, and they open up to the sides. Okay. Ours at the Hemlock locking crossing is a smaller dome, 16 foot in diameter, and this shutter opens up and over. Okay. But a lot of the bigger ones, matter of fact, if I go back, let me see, go back to that picture, that beautiful picture of, you see, there's the two doors that make up the slit right up here. And one goes to the side and the other one goes to that side. This one looks like an up and over type. Yeah, as a matter of fact, you can see it from that structure there. These two are the type that go up and over. You do need to have the opening to go a little bit beyond the zenith of the dome. I mean, the highest point in the dome. Because if you want to point the telescope straight up to look at something, you got to be able to have that part open. So it doesn't go right to the center, but it goes a little bit beyond. And there are different ways to accomplish that mechanically. Okay. Anyhow, so yeah, that telescope takes, once the slit is open, it'll probably take about 2-3 hours for everything to settle down. Even though they try to keep the temperature inside the dome the same as outside, we're talking about a big space. And yeah. So yeah.
I have a question about the dark sky. I probably when they selected that location, there wasn't that much light pollution in the area. Is that a problem now?
Oh yeah. It's definitely not like it was back then. And the other thing is that since then, we have built bigger and fancier telescopes in the, the parts like in California, and we'll be talking about different places where we have telescopes today. It seems like every 10, 15 years or so, there's a new mecca for telescopes. The place to build, and then they get all built there, and then someplace else. So it's not bad, but to be honest with you, the instrument is no longer, as a matter of fact, it doesn't belong to the University of Chicago anymore. Some years ago, we, meaning the astronomy folks, were terrified when we heard that the university was going to sell it, and they were going to make condominiums and a golf course. And everybody went, "Are you crazy?" Fortunately, the university sold it to a nonprofit foundation called the Future of Yerkes Observatory, something like that. And that is now they're running it as an educational. They bring kids to that, and students who are at the university can still use it. I mean, the instruments are still good, and the area isn't bad for observing. So students can use it and so forth. Yes, I understand that they reopened because of COVID. They reopened public tours last year. I have no idea, though, how you go. I mean, I'd say if you're interested, go to their website. They do have a website. Because in the old days, because it was belonged to the university, every Saturday morning was public tours, and it was free. I believe that they're charging something these days to take a tour, and they offer a number of tours. I understand there's one where there's only 12 people in the tour, and you spend the night in the dome observing through the telescope. I'm sure that's an expensive tour. So yeah, just say Yerkes Observatory, and you'll probably get to the website about tours and how it's operated nowadays. And, yeah. So yeah, it takes quite a while for that telescope to settle down and start looking through it. Also, the last time that I was there, I decided to use the so-called 39-inch, which is really a 40-inch reflector. And I was appalled in what poor shape that mirror was at. I said, "John, come on, this is pitiful. You mean you guys cannot afford to have this mirror resurfaced?" He says, "Well, it's not getting used much, and they don't want to spend the money on it. They want to spend on something else." I go, but I thought it was a shame to have such a nice instrument in such poor shape as far as the reflective surface of the mirror. So, yeah, if you happen to be in the kind of the southern part of Wisconsin, just to look at the building, I mean, you can just walk around the grounds for free. It's such an interesting building because the architecture that it will never be done again, gargoyles and columns, and pretty neat place, and beautiful grounds. Yeah. So nobody has been able to make a bigger lens than 40 inches. And I'll cover that when we talk about the different kinds. Was made, the blanks came from France. They have been made in France for a telescope they were going to build that they never built. They were purchased and brought to the States. There was a very famous optician called Clark and Sons. They did a lot of the big telescopes, and they ground the lenses. You know, they were American folks. They ground the lenses, build a cell, and then the different company that's the one who made the big structure. You know, the base and all that kind of stuff. Okay, reflecting telescopes. So who invented the reflecting telescope? Here we go again about inventing. Well, this is gentleman, James Gregory, as you can see, early part of 16 to the late 1600s. Or was it Sir Isaac Newton, 1642 to 1726? Good question. Well, let's talk about James Gregory. He came up with a different idea for a reflecting telescope, the Gregorian telescope. And when you asked me before about blockage of the secondary, so in his idea was to again have the primary at the back, But here in the front, he would have like an optical glass window, okay? A combination of glasses that would not affect the path of the light. The light comes in, hits the primary mirror on the back, gets reflected to the secondary that is attached to the back of that optical window, okay, in the center. That reflects the light right back toward the primary mirror through a hole in the center of the primary mirror and out the back end where you would have your eyepiece and your eyepiece holder to observe through. All right. Different idea for a telescope, getting away from the refractors. Except that, as you can see, it almost took, well, over 100 years, right? From 1565 when he designed it until 1673 when somebody, Robert Hooke, who was a telescope maker, made one that worked. Okay. Gregorian telescopes are still around. They're not as popular as they were one time, but they're still around. So what about, here's, by the way, is now this is not the original Hooke telescopes. It's a replica that was made probably somewhere in the 1800s. And it is in a museum today. Once again, this is not very big, as you can tell. If you see this lock here on the display window, you can compare the sizes. Probably it's about this big. Okay. Eyepiece back here, and the mirror will be in there, of course. This little knob is how you focus it. That you notice that the front section of the, I hate you. I'll give up on that. This section of the tube, as you turn the knob, goes in and out, and that's how you focus the instrument. Okay. The instruments in those days were made beautiful. Maybe they didn't work very good, but they were good-looking instruments. All this brass and again leather covering on the tube. And then we have the Newtonian telescope. So I'm a fan of Newton because he was into so many things. He did a lot of studies with light, okay, and about refraction and reflection and prisms and all that. Of course, we all know about the apple falling on his head, which is not really a true story, but that's okay. And telescopes. He got into telescopes as well. So he came out with the first really reflecting telescope that really worked well. It was a rather simple device, and that's the one that we know. The scope here, the optical part of the scope, is a Newtonian. Mirror in the bottom, little secondary in the front, hole on the side where you have the holder and the eyepiece. That's Newton's idea, and even nowadays we refer to them as Newtonian telescopes. So if I tell a fellow astronomer, I got a 12-inch Newtonian reflector, he knows exactly what my telescope looks like. It's after the design made by Newton. And because it was simple and could be built fairly simply, a lot of amateur telescope makers started making Newtonian reflectors. And there's a diagram, again, of how it works. We've seen this before. Open tube, light comes in, primary mirror on the back, reflected toward the front. Flat secondary mirror at a 45-degree angle reflects the light through a hole on the tube. And on that side is where we mount the focuser and the eyepiece, and we get to look through it. Does this block some of the light from reaching that? Absolutely. But in the Gregorian, if I may go back, in the Gregorian, same thing. The secondary mirror is in the center, and it blocks some of the light from reaching the primary. But that's okay, because the primary has a hole in there anyhow. So, okay, go back to Mr. Newton. That, again, is a replica of the original one. Nobody seems to know where the original one went to. But again, that replica was made like around 1820 20-something in the United States and donated to the museum where it is today in London. Newton, he did have an interesting idea, which some people had copied. This is different from the one I have, and I keep pushing the one button. You see the ball here, which is held kind of in tension by those two arms. Well, it allows you to move the telescope in any position. As a matter of fact, a friend of mine who was a member with me in Milwaukee, a tinkerer like me, and he decided to produce a commercial telescope and try to sell it. And he used this idea for the base. The telescope, the bottom of it is a sphere, and the mirror is in there, and then he's got the arms, and he stole a few of them. He did all right. But anyhow, that's how this one is mounted. Again, with this big kind of turnbuckle, that's how, again, he was moving this front part of the tube in and out for focusing. There's your eyepiece there. Not quite sure he made a boo-boo there, maybe, I don't know. And his spider is in there somewhere. Yeah, I've always been captivated. Why is that dark spot there? Heavens knows. Well, whoever, I presume that whoever made the copy made it an exact copy. So whatever that may have been, I wonder if he was trying to find another way to deal with the light, which is not impossible. So the advantage of why nowadays we no longer make big refracting telescopes. Yeah, sure, you can still buy small refractors. The amateurs use some prefer refractors over reflectors. I will say that for planetary work, probably a refractor overall, if the qualities are the same, is slightly better than the reflector. Maybe because that secondary is not there in the front, messing around with the light a little bit. But again, big refractors, no, those are, the 40-inch was it. And we'll see why, actually. So the size. Okay, so the 40-inch lens for the Yerkes telescope weighs 500 pounds. 500 pounds of glass up there. We all know that in order to support a lens, those of you who wear glasses, maybe not, mine doesn't have a frame, what do you call it? Yeah, they don't have a frame really. Very nice and light. But this lady here has regular frames all the way around. The only way to support a lens is around the perimeter, right? You cannot support it like from the back because it blocks the light. And the mirror, the lenses that make up telescopes mirror, they're not very, they're fairly thin, but they still get heavy. But because they're thin, they start collapsing on their own weight. All right. And it doesn't take much to change the shape that you need in the lens. Okay. And the 40-inch was it. No, Alban Clarkson figured out how to grind it, how to shape it, so it worked. But from that point on, nobody else has been able to produce a 40-inch or bigger that worked. They tried one in, I think, in France, and they never went anywhere. I think the blanks were in exhibition at one of the welfares or something like that. But after that, they just got rid of it. It was never made. So that's why the 40 is still the biggest in the world. So we have the problem with the lens that they will sag and the shape will change as they get heavier and heavier and larger. On the other hand, the mirror, and the mirror that went around, I'll use this cover. If this is the reflective surface, we're supporting it from the back. We can support it from the back any way we want to, okay? And by the way, some of those supports, it's called a cell. Whatever you attach the mirror to is called a cell, and then the cell gets installed in the tube. Okay? Some of these cells for the big mirrors are wonders of engineering. They have multiple pads, okay, to support the mirror, attached to all kinds of levers and counterweights and all that. So regardless of the position of the mirror, and you have to realize that as as I take my telescope, I'm sorry if I'm moving a lot for you. If I, I can tear, up and down like that, right? The mirror's back here, so it's nice and flat. Here is standing, well, it would be almost like standing on the edge and so forth. So the mass of the telescope, of the mirror, is getting shifted around. If you actually allow all that weight to actually be on the edge of the mirror, you would, again, because of the weight, you would change the shape of the surface. But these mounts are able to compensate, so that regardless of where the mirror is pointing at, the weight is equally distributed through the whole mirror, and therefore the mirror doesn't flex. In the smaller mirror telescope, you don't need that. As long as you have a good support, that's fine. But when you start getting, you're talking about a mirror that weighs tons, it becomes a big to-do. The other thing is the labor required. To make a lens, you have to grind both sides, right? You have to grind them and polish them and all that. While with a telescope, with a mirror, of course, you only have to do one side. Okay, so there's a lot less work that has to go into making a telescope mirror versus a lens for a telescope. That's why we have all these gigantic reflectors nowadays. But let's not get ahead of ourselves with that. Early mirrors. Before we were able to make this big glass blanks, where they were using metal mirrors. There's a mixture, that's not the right word for it, but anyhow, for a metal, that's called speculum. And as you can see, it uses 2/3 is copper and 1/3 is tin. Okay. This material can be polished, ground fairly easy. It can then, by polishing, get a very reflective surface. It's just like a mirror made out of glass nowadays and aluminized. Okay. They did have a little bit there. Oh, by the way, yeah, it is an alloy. That's the word I couldn't think of. It's whitish in color. It's very brittle. You drop it, it breaks into many pieces, even though it's metal. Okay. But again, you can polish it to the point that it's highly reflective, just like an aluminized mirror would be. The problem is, it tarnishes very fast. Again, back in those days, they hadn't quite come up with the idea of put some kind of coating on it, okay, to prevent it from tarnishing. I mean, I'm talking 17th century, okay, when the speculum was being used for telescopes, 17, 18. So what would happen is most observatories will have two. One would be in the telescope that they're using. The other one is at the lab being polished. And then they would swap them. When the one on the scope started getting tarnished, take it out, put the other one in. So get back and forth all the time, cleaning this metal mirrors. You heard of Mr. Foucault, the pendulum guy? Okay. He's the one who introduced this whole idea of using glass and using silver deposited on the glass as the reflecting surface. So the whole thing about silver in mirrors, and by the way, back then the mirrors in the bathroom were silver behind them. Until all the materials were found that, of course, worked just as well and weren't quite as expensive as silver. The aluminized mirror that we know today actually didn't develop, as you can see, until about 1932. So it's a fairly recent idea to aluminize. And then when that other mirror was around, that one has something called beryl. I think I mentioned that before, a different kind of reflective material. Okay, so now we're going to go on to, we're starting making big telescopes, not the 12-inch, not the 20-inch, but now we're starting getting big. So Hale was trying to determine, is the Milky Way it? is the universe the Milky Way? Or is there more beyond that? And he needed a big telescope to be able to photograph and observe that type of thing, okay? So therefore, he was a big proponent of building large telescopes. And Hale was pretty good at it, about getting people to give him money to do things. I have to give him credit for that. In 1908, that is, they finally were able to make a 60-inch reflecting telescope. Okay. I installed at Mount Wilson Observatory, that's in California. Okay. Mount Wilson is in Los Angeles County. Actually, the observatory is not too far from Pasadena. The 60-inch then was capable of gathering more light than even the 40. Okay. Remember, we talk about surface area. As you increase diameter, you get more and more area from which to collect your light. But that wasn't good enough. Of course, Hale wanted something bigger. So I figured by 1917, he had been able to talk Mr. Carnegie into giving him money to build a 100-inch telescope called the Hooker telescope, which is also in Mount Wilson. Those instruments are still there. If you happen to visit Mount Wilson, you can tour them and actually see them. A kind of an interesting instruments here. So here is a 16-inch telescope. Pretty much the way it's mounted, notice that it's an open frame tube, okay? That's fine as long as you don't have light. I mean, those spotlights are so they could take the picture, but as long as you don't have problems with the light coming from all the directions, the open frame makes the tube a lot lighter, which solves the problem for the engineer. But that telescope is pretty much like me. If I take this Dobsonian mount that we talked about last week, and this is pointing to the pole star, now I have an equatorial mount, just like the 60-inch instrument. You know, same idea. It would go like this, and this, and like so. And again, the open tube. Notice that the sheet, you said, Willikers, this thing, I mean, you're supporting all the weight up front. Well, yeah, but the 16-inch mirror is here. That's a heavy guy. You have the open frame structure for the tube, which makes it lighter. So it bounces. I got to learn to stay in one place. No. Okay. And here is the 100-inch Hooker. Another kind of interesting mounting. This is called the modified horseshoe. It's pretty much like a rectangular box with supports at either end, even though this becomes the polar shaft. And then the telescope swings inside of it. Notice that this scope, you could not point it to the pole star because you would need for this tube to be, lined up with that, and this kind of gets in the way. But that's okay. They find different ways to align it. Hale wasn't interested in looking at Polaris. He wanted to look like some of the other galaxies, what we thought were galaxies, or these fuzzy things, to determine if there were other galaxies like the Milky Way galaxy or not. The so-called island universe was one idea one time, but the Milky Way was it. The Milky Way was the universe. And Hale said, I don't think so. I think there's more to it than that. So we keep getting bigger. In 1920, Hale then started looking for money to build a 200-inch telescope. The famous 200-inch telescope at Palomar Observatory in California. You may have heard of that. By 28, Rockefeller Foundation had given him the money to build a scope. Now the problem was, how do we make the 200-inch mirror? Because nobody knows how to do that. And some people say it cannot be done. Yeah. The technology wasn't there at the time. to make that kind of a glass blank. But after a lot of failures with different experiments, he ended up in 1929. Hale went to the Corning Glass Works in Corning, New York. Anybody ever been there? If you ever get to go to Corning, New York, definitely make it a point to visit the glass museum that Corning has. It's simply amazing. And one of the things you're going to see in display is the first mirror that they tried to make. That didn't. The one in the telescope is the second mirror. But Corning took on the challenge. Corning had developed Pyrex glass, right? If you have a Corel cookware at home, and some of the other dishwares and all that, they were the ones to finally invent this combination of glass and ceramics into one thing to make all these pots and dishes and so forth. The specifications for the blank: 200 inches in diameter, 5.1 meters. The area of this mirror then will yield 31,000 square inches. And you have the number there for the square meters. The weight, 20 tons. 20 tons of glass. One big chunk. The material, of course, Pyrex, that was developed by Corning. The temperature, the melting temperature for the Pyrex is 2,700 degrees Fahrenheit. So that's how hot they got to get the compounds that make Pyrex before they liquefy and become one homogeneous mixture. Now, annealing. Annealing is a process it's used with metals and so forth of how once you make, let's say the mirror or something out of metal, how slowly do you cool it down so that all the crystalline structures form properly, and that also affects the hardness of the material and so forth. So we anneal metals to make them softer so they can be worked on, or then a different heating method to make them hard again. So a lot of the parts in the engine in your car, you have to realize got to be hard to take the punishment of an engine. But they have to be made soft when you're trying to make it. It would take at least a year for this glass mirror, once it was poured, to slowly cool it down over a period of time so that it wouldn't crack or anything like that. Okay. Now, I like baking. I like to make cheesecakes once in a while. Anybody here makes cheesecakes? You used to? Okay. So for a cheesecake maker, one of the biggest challenges is when it's cooling down, that it doesn't crack on the top, right? Okay. And the reason for that is, of course, that the outside cools faster than the inside, right? The inside of the cake is still hot. And though the heat wants to rise and get out, and usually end up with a crack, which I usually cover with the strawberry stuff that I put on top. I had come up with different methods trying to see if I can prevent the cracking. Sometimes it works, sometimes it doesn't work. But that's a problem when it comes to mirrors. You're talking such a mass of glass that it has to be handled very, and we'll talk about some mirror makings in a little bit. Grinding and polishing. It took 11 years to grind and polish the mirror. Remember, you start grinding this piece of glass, and what do you think happens to the temperature? If the temperature goes up, the glass, even though it's Pyrex, which has a very, very low coefficient of expansion, still will expand. So you got to stop, let it cool down, and then you go at it again. It's a grinding process. I had ground telescope mirrors. We take a 55-gallon drum, fill it up with water, screw to it a piece of wood, secure the mirror blank with whatever it takes to secure it in place. Take a piece of ground, just plain old plate glass, okay, same diameter. You put a solution of grinding compounds, different sizes, in a slurry of water. You put that on the primary mirror or on the mirror itself, or what's going to be the mirror, put the plate glass on top, and then you follow a sequence of different moves, like in and out, in and out. I do 5, I take 1 step. 5, I take 1 step. 5, I take 1 step. And I do that for hours and hours. Once you start with really coarse carborundum or some compound, and so you can fast start getting down to the curve, you know. Then when you're done with that, you go to a smaller particle and a smaller particle and a smaller particle. Now you start getting into polishing, so it's super smooth. We use, you ever heard of jeweler's rouge? It's almost like a lipstick, but it is an abrasive, and we polish with that. So after you have walked miles and miles around this 55-gallon drum, and you continuously, you do it, you test the mirror. There's devices you can use to test it. How am I doing? Am I getting close to the curve I need? Nah, the edges aren't good enough. Go back and try to correct that. Grind, 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 test, grind, 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 test. 300 hours, 400 hours, easily, depending on the size of the mirror you're working with. That's the manual way to do it. And that's how these guys were making most of it. A lot of it was by hand. They did make some machines to help them a little bit. But, so 11 years. In the process, they removed 5 tons of glass out of the 20 because you want that shape, right? They use over 62,000 pounds of different abrasives to grind it. And the reflective surface, the reflective surface, the aluminum that they deposited on it is only 3/1000 of an inch thick. 3,000, if you're a machinist, you're always working in thousandths of an inch. We're talking about a teeny tiny. Okay. Here's a picture of the Hale 200-inch telescope. It is mounted on a true horseshoe mount. You see how this whole thing is a big horseshoe, and the telescope can be pointed directly at the pole because of the shape here. And this whole horseshoe rotates on a film of oil. This oil being pumped into the bearing surfaces here, a high pressure, and that's what the whole telescope, which weighs, I don't know how many, I should look to see how many tons the whole thing weighs. That's how it's turned by a teeny tiny motor, because there's hardly any friction. Okay. If you go to California, you can at the Mount Palomar, you can actually go and look at this telescope. It's have public tours. Do you see that person? Just to give you an idea, you see this gentleman here? Okay, get an idea of the size of this behemoth. Oh, it's like a maybe 1,000 cup. It floats. All that tons and tons of stuff are floating in a super thin film of oil. And you can actually grab it and move it when you take off the brakes. Yeah, it's amazing, isn't it? This is what the building looks like. You can see that the slit doors are open. You notice that all domes are painted white. As a matter of fact, there's a special white paint for observatory domes that among the many things in it is titanium powder to make it as reflective as possible to get rid of the sunlight in the summertime, the heat from the sun in the summertime. So I don't think you'll ever find a dome painted black. That's unless some top secret military thing for who knows what. Here's a shot. There's the 200-inch. Eventually, that coating, like you saw in the little mirror that was going around, is damaged by weather and so forth to the point that it has to be replaced. Okay. Big observatories don't take off their big mirror and send it to a lab somewhere. That's too much of a risk that it might get broken somewhere along the lines. So the big observatories have their own facilities at the observatory to strip the old coating and put on a brand new coating and put the telescope back in action. The technicians, that's what they're doing right now. They are in the process of removing the coating. And you can see the clear glass. You see the honeycomb structure in the back? I mean, the front of the mirror, of course, is solid. But you see this honeycomb in the, well, that's in the back side. And it's done for a couple of things. First, it makes the mirror lighter. And also gives you the places to attach all these supports that are going to support and compensate the motion of the telescope. The honeycomb, because the bees are super smart, is a very fantastic structure when it comes to weight distribution. Aren't they smart, those bees? And we copy it from them because, hey, what the heck? You don't have to reinvent the wheel. By the way, I think I mentioned it before, that we use among the many coatings, the silicon monoxide is one that's very popular for protecting the aluminum or whatever material they might be using. I'm sure they have some sophisticated reflective material on that telescope. I told you that places become popular. So in 1960, we discovered that the top of Mount Mauna Kea, that you have two volcanoes in, I think it's in the island of Hawaii. One is Mauna Kea, Mauna Loa. Mauna Loa is still active, but Mauna Kea is an extinct volcano. And they said, you know, this is a great place to put an observatory. Dark skies, really dark skies. No light pollution, at least not then. And I think they work very closely with the whole state about, hey, we gotta keep your lights. A special, I think I talked about, if you have a well-designed fixture for your light, you can put the light where you want it and don't throw it around all over the place. So they definitely work closely with them on that. Good seeing. Seeing is a word that we use to describe the quality of the air at any given time, okay? Scale from 1 to 10. A 1 means that, boy, the sky is clear as can be, no clouds, very little pollutants in the atmosphere, very little motion of air masses in the atmosphere, and therefore it's going to be as good as it gets as far as observing through a telescope. You notice that stars twinkle? Okay, I presume, if you look at it. It has nothing to do with the star. The twinkling is produced by the different masses of air in our atmosphere at different temperatures. We have cold air dropping, hot air rising. So it's like a big washing machine in our atmosphere of air moving around. So when you see a lot of twinkling, that means that it's a lot of motion going on up there. On one of those nice, super cold winter nights, when the change in temperature from daytime to nighttime has not been significant, as long as it is clear, it's going to be a good observing night. You'll notice that the stars don't twinkle as much as they do at other times. So that will be a number 1. And then when it gets really bad, it can be to 10, and that means you stay at home, you go to the observatory, and you read your astronomy books that night. Okay. Because of the elevation, 13,796 feet is above most of the humidity in the atmosphere. Humidity does affect our views. Okay. Clean air, good weather, is close to the equator, so they can catch things on either northern hemisphere or southern hemisphere. Anyhow, that was the place to be. Everybody wanted to build a telescope there. By the way, that mountain is sacred to the Hawaiians, so there's been a lot of problem between the astronomers and the Hawaiians. You know, at first said, sure, you can build one. Well, guess what? Today, we have 12 different facilities housing 13 telescopes on the top of Mauna Kea. And they're run by all these countries. It's not just the USA, but a lot of countries have telescopes there. Again, because of how good the conditions are for observing. Little side story, good friend of mine, he's passed away now. He was probably one of the, if not the original members of the Milwaukee Astronomical Society. He joined shortly after it got formed. Retired mechanical engineer. fantastic guy, very knowledgeable. He did retire and moved to Hawaii. That's what they always wanted to do, him and his wife. One day he's reading the paper. Oh, I forget which observatory is looking for an engineer to work part-time. Off he went. He got the job, and he was having a great time playing with this gigantic telescopes. I mean, who can ask for anything more? Well, he told me, said, you know, it snows up there. You know, after all, it's 13,000 feet, almost 14,000. We get snowstorms. We can get some horrific winds up here. He says, our wind indicator has disappeared about 4 different times. We have some really high winds that come out in the morning. The only thing left is the wire dangling in the wind. The mast is gone. The instrument is gone. He just blown away. Who knows where? I thought that was interesting. He got stuck there a few times where, of course, when it's snowing that badly, you're going to come down this road, you know, that zigzags. As a matter of fact, here comes a picture. Look at all those telescopes. It's like going to a popular discotheque. Everybody wants to go to that one. And the winding road to get way up there, 13,000 feet. So yeah, on a snowy day, I don't think you want to try to. As a matter of fact, a lot of times they close the road, of course. All kinds of telescopes. One of my favorite things, a revolutionary idea. A gentleman by the name of Roger Angel. As you can see, he was born in England, but from American parents. So he still heads the Stewart Observatory Mirror Laboratory. It's at the University of Arizona in Tucson. Okay, but Roger came up with an idea. He says, if I could rotate the kiln in which I'm trying to make melt down the glass to make a mirror, if I can spin it at the right speed, and I kind control the temperature, when all the components actually become liquid because of the spin, somewhere will go up to the sides, and I'll get, it may not be a perfect parabolic surface, but I get a cave. And imagine all the time I'm going to save from grinding away, right? So what's his idea, that he could come to do that. A lot of people say, you're nuts, it's not going to work. I remember when the first was getting published, I was still living in Milwaukee, I think, at the time. Okay. People said, nah, you're crazy, that's never going to work. But Roger stuck to his idea. Again, if you're outlandish, you're a fool, you name it, all kinds of articles about his idea. In 1985, they got enough money to build a kiln. It was right underneath the stadium at the university. That's the only place they could find to build it, I guess, so that it wouldn't cost them any money. And the first one sprang a leak in the mold, but it proved that it could be done. Okay. So that brings us to where they are today. There's a telescope being built called the Magellan telescope. It will be the biggest one in the world at that time. Okay. It's been built in the Las Campanas, which means the Bells Observatory. It's in the southern part of the Atacama Desert in Chile at around 8,200 feet. Chile now is the mecca to build telescopes. Needless to say that the weather conditions are amazing, okay? Clear skies, no humidity, blah, 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 no pollution. Right now, as I'm speaking to you, this 7th and final mirror, this telescope uses multiple mirrors. From the light from each mirror then can be concentrated to give you the appearance of a gigantic mirror. And we're going to be looking at sizes and all that. So right now, the last one, number 7, is being polished at the optical lab in Arizona. Okay. I was in Tucson in 2014 to visit some friends. And needless to say, I had to go to the optical lab. And when I was there, the mirror number 4 was being polished. I'll show you some pictures. Being Tucson, that means the Kitt Peak National Observatory is not too far from Tucson. Of course, I got to go there. It's like going to Mecca for astronomers. You bow in front of the telescope. Quite a place. The city of Tucson has always been very good to work with the observatory about their lighting. They have changed their city lighting completely a couple of times as the new things came on board. Because definitely the pollution as the city of Tucson grows, I should say, affects what's going on at the observatory, the research going on in the observatory. I could not believe it in 2014 when I went to Tucson, how it had grown. From what I remember from maybe about 10 years earlier than that, where it was just a quiet little university town. Now they're building houses up the mountains, up you name it. The 6-lane highway, crazy people driving all over the place, mini malls all over Kingdom Come. You know, to me, I understand people want to live there and all that, but what a shame. I mean, such a beautiful area, you know, with the mountains and all that, and it's getting commercialized. And remember, I told you I was an old romantic, so we gotta make. Okay, so each mirror, 27.6 feet in diameter. Each mirror. Okay. When you combine all 7 of them, they will yield something that looks like a mirror with an area of 3,960 square feet. I'm talking about a big surface. Everything is computerized nowadays. These mirrors, which are fairly thin compared to the like hail that was thick, that's why it weighed 20 tons. They have actuators in the mounting for each mirror that they're continuously, physically changing the shape of the telescope to adapt for what's happening with the atmosphere. It's called adaptive optics. It's one of the newer developments in telescope making, in big telescope making. Okay. So that it can be as perfect can be. Okay. The mirrors, kind of interesting. The sand that they use to make the glass comes from the Gulf of Florida. Yeah. Not my backyard, not lakefront, but it has to be that sand from that spot. The sand gets shipped to Japan. The Ohara Glass Works in Japan, probably one of the best glass makers for telescope purposes. Okay, make something called borosilicate glass. Okay, melting point is over 1,000 feet Fahrenheit, degrees Fahrenheit. Okay, is boron oxide that they add to it. If you're a chemist, you know, I'm not a chemist really, to be honest with you, and it's what gives it the low index of expansion. Right? We want a glass that doesn't really expand as slow as possible with changes in temperature. Pyrex did that, and when Pyrex developed that glass, wow, now we can make cooking pots out of it. Before that, you couldn't take a glass, a plain old glass thing, stick it in the oven, take it out, and it would proceed to crack on you. I had a Pyrex glass crack on me, a pie plate made out of Pyrex. Took it out of the oven, put it on top of the stove, and it shattered into 1,000,000 pieces. There was a it was a defective one, which I never saw. There was a teeny tiny air bubble in the glass. That's a no-no. I'm surprised that it passed their inspection. And when that glass contracted, when the air contracted, when it cooled down, it pulled the glass and cracked it and broke it. It was quite a spectacle. Anyhow, going back to the Ohara Glass Works. So they're the ones who make the special glass. Do you know about a way of making ceramic pots? It's called the coiling effect. Natives in any part of the world have used that technique for forever, right? So they hand make these coiled pots, okay? Each one capable of holding a ton of glass. The big pots, I've seen pictures of them, they're pretty big. They fire them in the kiln like you would fire any kind of ceramic, okay? In goes all the components to make the glass in each pot. They get put in the kiln. Finally melts down, it becomes glass, then they cool it at the appropriate temperature, on their appropriate period of time. They take it out, they break the pot. It's a one-time use pot. They break the pots, and any glass in the outside of this bowl of glass that has contacted the clay pot gets discarded because it's got impurities in it. So they throw that away. And then they break the good glass into chunks about the size of a grapefruit, and each piece is inspected under a microscope, looking for cracks, any bubbles, any impurities that might be. If they find one that they don't like, that gets thrown away too. And then finally, all the glass that passes inspection goes to Roger Angel in Tucson. And that's, again, talked about the contaminants and so forth. Here is a diagram, or actually a model that was made when they were designing the telescope. Please notice the man, or the human figure there. Give you an idea of the size of this thing. All 6 telescopes, all 7 mirrors, like everything else, the light will come and hit each mirror. They'll be reflected to the secondary way up there on the top. There's a secondary for each mirror. And then all that light gets combined and reflected right back through the hole in the center mirror to all the instrumentation that will be attached. You don't look through an eyepiece with this telescope. Sorry, I wish we could. They got monitors, they got spectrometers, they got photometers, they got all kinds of different things that they use for the research. Here's a photo at the optical lab back in Tucson where they're filling up the mold. There's the guys putting who knows how many chunks of glass in this thing. Don't want to touch anything that you don't have to, so that's why they got all kinds of special gurneys and all that to support them as they go around putting the glass in the mold. There is a spinning oven. It has a lid that has come down. They start spinning it, and they start heating the piece of glass, and they control the whole process until it liquefies, and then monitor to see if it's getting the shape that they want to get close to. Okay. When they're happy with that, they start reducing the temperature very, very slowly, period of weeks at times or more. And then eventually they will open up, of course, stop the oven, open it up, and take out the question. Yes, sir.
Is the heat generated electrically or?
Yes, sir. Electrically. Is the best way to really control minute changes. Yeah. All the things don't respond as quickly as an electric heater. Yeah.
I have one other.
Yeah,
I
yes,
know
sir.
our time is about up, but
That's all right.
wondered if you could spend a minute. I know there's another class later this semester about the James Webb telescope, but could
Okay.
you spend a minute telling us about the James Webb?
Well,
What
okay.
kind of mirrors?
The James Webb has their mirrors are made of titanium, I believe. That's what they use for the mirrors, if my memory serves me right. And the reflective surface is gold. And as you know, the biggest problem was the temperature. Okay, the instruments, a lot of the instruments that we use have to be kept very cold. As a matter of fact, some of them use like liquid nitrogen to keep the piece of equipment super cold. It has to do with as the temperature goes up, no, what we call noise in electronics goes up, and that interferes with what you're trying to do. So that's why a super cool detector works better. That's no problem at outer space, right? It's almost absolute zero. But that's why they have this fantastic shade, divides of 7 different, always facing to the sun. They don't let the detectors look at the sun ever, you know. So it's always, that's why it moves in its orbit at the like the one point out in the orbit of the Earth. I just went blank. I should remember this all the time. L1, yeah, but the L stands for Lagrange points. Yeah, there are 4 Lagrange points in any two-body orbiting thing that where they're very steady to put something at. Okay, so
One of the things that I'm impressed with is that right here,
oh,
they send those, what are there, 16 mirrors, something like that, the hex.
the mirrors.
And they send those in a stack in the satellite. And it gets out there and they're assembled in space.
Oh, well, this
And
one.
then that screen that you're talking about
Mhm.
is microns thick.
Oh, yeah. Well, it's like Mylar.
When it unfolds into the size of a tennis court.
Mhm.
And it's
Ah.
got servo motors that will keep it in line for protection.
And tighten
But
it up.
even starlight temperatures will affect the thing. It's really amazing how they can put that whole thing up in a very small refrigerator or multiple refrigerator size package
Yeah.
and build this huge complex mirror and build the protections for it and be able to aim at all the servos and everything that have to be used. That thing is just mind-boggling to even think about how they could assemble that thing in space.
Well, I don't want to tell you much about it because, you know, I don't want to spoil your guess, but it's a folding. It was made as a folding. The arms open up and all the mirrors are there. And they had to be, I think, like around 450 separate things that had to happen for the thing to, and if one of them went wrong, bye-bye, it's gone, right? And remember, right now, we cannot go out there and fix it like we used to do with Hubble, so. Mm-hmm. Yeah. Mm-hmm. Right. No, it'll be, like I said, you should have an interesting talk when that whoever comes to give you the lecture about. It's an amazing piece of technology for one thing, you know. Here you have one mirror being polished. The way this thing works, and I'm sorry I don't have a video for it, the whole mirror is slowly going around, right? That small circular piece with all kinds of pads and different chemicals in there is rotating, and it's traveling back and forth on that black arm that you see there. The mirror's going around, the thing is polishing, and it's going back and forth, and it's all computer control, of course, to follow the formula that they're using for the mirror. I have a close-up of the polishing head. There it is. All those little pads and actuators to apply the right pressure, the right angle, the right amount of whatever you're using at the time for polishing compound. Yeah. And I think I have another picture for you. Yeah, I always thought that it was funny. There's a guy with a mop on this almost priceless mirror, but I'm sure it's the right kind of a mop, you know. At this point, they're starting and that's just the beginning of the cleaning process before they think of actually putting the reflective coating on. But I say, I got to take a picture of this guy with a mop. No mask, no nothing. Well, again, it's because they're just beginning to remove all that all the grit and all that is on it right now. They're not too concerned at this point, I guess. But you can see the honeycomb structure in the back of the mirror. Amazing. And that brings me to the end. This is the.
Thank you so much.
Thank you. That is a telescope at Hemlock Crossing. made by a company called Meade. It's a 16-inch catadioptic telescope. It uses a combination of lenses and mirrors. It's something like that Gregorian telescope I told you before. Okay. So yeah, the light comes in the front, hits the mirror in the back, goes back to the front, hits the secondary mirror. The light comes through the hole in the center of the primary out to the eyepiece, which, as you can tell, is the eyepiece holder. And I'm trying. Oh, there's this pad here that's connected is the one that we communicate with the telescope to tell them what we want to see and what to do.
Once,
This is we have only one finder scope, which is this little guy here, which we don't use very. I'll tell you something. This animal back here that looks like a bigger telescope is really something called a star lock. It's a device invented by the people from Meade. When we use it, and to be honest with you, I don't use it when we're just doing general observing to the public. But now we want to talk about taking photographs. Now we got to be dead on, right? Once you turn that instrument on, once you find whatever you're looking at in the sky, that, let's call it a telescope, looks for the brightest thing you can see in that field. Okay. It locks on it, and it takes over the control of the motions of the telescope and stays dead on that object, so that over a long exposure or a long period of time, it stays right on it. I don't need that when we're just observing, especially you go up, you look, okay, next, you know. But when we want to take a photograph and do long exposures, then we definitely want to be dead on so we don't see any motion. You know, if your stars start getting a little elongated, and then when you take your photo, you know that something is not tracking properly. Hemlock Crossing County Park. We finished building it last year. Actually, it was like last September. Of course, this pedestal here was a portoscope. It's attached to this concrete pier that goes down below the truss line. The floor on the observatory, you notice this darker color thing around it? The floor of the observatory cannot touch the concrete pier for the telescope. If it did, and I'm looking through the telescope and you're walking in the observatory, earthquake. Okay. So that's a special insulating blanket to isolate that pier from everything else. Nothing in the observatory touches. You can see a couple of the motor units that turn the dome around. And of course, we have a slit that opens up. So the rotation and the opening up of the slit is all electrically controlled.
Frank?
Yes, sir.
Oh.
Yeah, we're done. So any questions? And
So there's been a lot of discussion about Starlink satellites and the problems with
yes, I hate them.
astronomy. Tell me.
Unfortunately, Musk decided that he needed to start a company to provide internet via satellites. And his idea was to put about 450 of these things up in the sky. Of course, any reflected surface in a satellite reflects light. That's how we see them, you know, they reflect the sunlight. It's interfering with all kinds of research because, you know, you're taking a picture or you're taking any kind of measurement of a star, and also one of the silly things goes across and ruins everything. Right now, it was about a month ago or so that he released the next batch. There was like 70 of them released at one time. And we started getting UFO reports because at nighttime, if you happen to be looking at the right time, it looks like a string of pearls across the sky. Anybody here seen it? I've seen it a couple of times. At first, when the satellites get released, they're close together. Eventually, they'll spread out to the designated spot in their orbit. But there's still going to be all these things up there. He said that he was going to put some kind of shield so that it wouldn't reflect light, and he hasn't done that. So they're a pain. Oh, yeah, eventually, they're talking thousands, yeah. And they're low Earth orbit, so, they could reflect more light. So, yeah, I wish they hadn't allowed them to do that, but, so now we're putting things out in space and, I'm waiting for a telescope on the moon. Can you imagine a big telescope on the moon, no atmosphere to deal with? It can be operated remotely, but that instrument would probably be amazing. And I'm sure it's going to happen, probably. I won't be around then, but I'm sure eventually something will happen with a telescope. They talked about the same thing with the radio telescopes, and they want to put them in the dark side of the moon, so it's not affected by all the transmissions that we have going on from Earth. That would be pretty interesting too.
I will share an anecdote with you. In 2017, I was basking in the sun on a beach on the northwestern tip of the island of Hawaii. And 82-degree weather, beautiful sunshine. I received a phone call. Yes, I had a signal there. I received a phone call and the woman said, "Mr. Morel, you booked a trip this afternoon to the summit of Mauna Kea. I regret to inform you that the trip has been canceled because of a snowstorm."
It's true.
So I wanted vengeance. I went back this year, and as I was coming out of a grocery store, I got into my car in the parking lot. The phone rang, and the woman said, "Mr. Morel, you booked a trip to the summit of Mauna Kea this afternoon. I regret to inform you that the rangers have closed the road because of high winds." I don't know if I should make a third attempt or not.
Oh, stick to it. You have to overcome weather, Mother Nature, as we refer to her.
Yes.
But Mother Nature does rule. I'm sorry, but she does. Yes. Oh, yeah? You were there? Oh, I'm sure, an amazing view of that mountain and all the instruments, huh? Oh, at sunset. Wow. Right. Great. Isn't it? I'm sure it was. Yeah, people who go to work in those, they have to acclimate to the altitude because of the lack of or reduced amounts of oxygen. So they usually had to spend some periods of time in that 9,000-foot level. Yeah. Is that what they recommend? And then you can start moving up. Yeah. But so if you start getting tired up there, and that's the reason for it. Not enough oxygen. Yeah.
Hold on a second here.
I'm just curious about Kit Peak. About 15 years ago, I was at Kit Peak and they were building a new style dome that was supposed to be radically designed differently to allow much more clarity.
Huh.
I just wondered if you knew anything about that.
No, I'm not familiar
Kit Peak
with-
has what, 12 or
Oh,
more domes?
they
But
got
this was brand new, was just being built. They had a whole explanation of the main differences and everything.
no, what year was that?
About 15 years ago.
15 years. Okay, well, I can look to see. I cannot remember offhand. I know they had one of the biggest solar telescopes there, and it's quite a telescope, I guess, like telescoping quotes.
Yeah, the Sunscope on near El Paso, I understand, is being closed.
Oh, is it the collector or solar scope, or is it
The one for the sun.
to collect sunlight?
Yeah,
Okay.
they're closing that.
Oh, that's too bad. Oh,
Last summer, lack of funding perhaps.
well, yeah, that happens.
Last summer, you spent some time at the Kennedy Space Center. Can you tell us what your purpose was for being there?
So as you said earlier today, I am a member of the Civil Air Patrol, the auxiliary of the Air Force. I have several specialties within CAP. We're pretty much set up just like the regular Air Force, the way that it works. And I'm a lieutenant colonel in the Civil Air Patrol, not in the Air Force, because I'm not I am a civilian. Anybody who belongs to the Civil Air Patrol is still a civilian. We're not part of the military. But we do missions for the Air Force. Okay. Anyhow, without getting into it, because you asked me that maybe I'll do a program about CAP sometime. Okay. I went there as a airspace education officer. That is one of my specialties. Okay. It is my job to teach our own people about aerospace, and aerospace covers everything under the sun. It's not just about flying airplanes and rocketry, but it has to do with physics and astrophysics and chemistry and physiology, how flight affects the human body. All those things are under this umbrella called aerospace education. Nowadays, I guess we call it STEM, right? Sort of, because STEM is sort of the same idea. But CAP has been calling that for forever as aerospace education. My job was to teach aerospace education officers from throughout the country. And for this year, it was at the Kennedy Space Center, in part because one of our members, who is an aerospace education officer, a good friend of mine, who lives in Florida, worked for NASA, and he was a true rocket scientist. And so he arranged for CAP to be able to use the facilities there. What a place to go to, right? So we were there, we had a great time, a great school, got to see a lot of interesting things. We were inside the assembly building, crawling all over the place, and they allow us to do that. So, well, that was my reason there. I've been doing that for quite some time now, being an instructor at that school. It's a national school held once a year. Yeah. Except during COVID, we had to go online type thing, but we're back to face-to-face classes.
Any other questions? I want to remind you that if you have not registered yet, you should consider registering for Professor Gonthier's presentation on the James Webb Telescope coming up in 2 weeks, I believe. 27, 1 o'clock in the afternoon. So register, should be very interesting indeed.
I started with New York Telephone in Manhattan.